Well, I guess we can start a little bit early, about 10 seconds. Welcome back, everyone. So we're nearly done with Chapter 9. Our purpose of Chapter 9 is not really to say all there is to say about differential equations, but just enough to get a view for the topic and see what some quick methods are in solving those equations, as well as a couple of applications. So we're going to complete section 9.3 today, possibly start 9.5, and 9.5 is going to be the final section in Chapter 9. After that, we're going to embark on the journey in Chapter 11, which is one of the longer chapters, but the exam will only cover up to 11.2, possibly 11.3. Any questions then about that stuff before we start today?
That's not next week, it's the week after, right?
Correct, yeah. So we still have midterm weeks next week, and that means the sample exam and information on notes that will be provided on the sample exam will be posted very soon, possibly over this weekend. Other questions so far about that? Okay, so then before we start, any questions folks have on the assignment that's coming due today? How are those surface areas and centroids treating folks? Not too bad? They're kind of awful, but one thing to keep in mind is in section 8.1, 8.2, really algebra was the worst part. So if you're worried about that on an exam where it's a timed 75-minute session, keep in mind that problems are going to be written so that the algebra itself is minimized, and it'll be focusing on just getting through the calculus portions. You'll get a feel for what the kind of questions look like once the sample exams are posted, which will be very soon. But let's go off then to separable equations. We only just barely started 9.3, so let's start today by reminding ourselves of the definition. Then we'll look at some problems that we can solve that are of the separable type. So our definition is that a differential equation is said to be separable if it can be expressed in the form dy dx is equal to g of x times f of y. So that's our working definition and the way we can detect whether an equation is separable or not. The formula is interesting. The left-hand side is the usual stuff. We have a derivative. So this would be a first-order differential equation. And it'll be the same situation in section 9.5. The right-hand side is kind of a weird way to write the definition, but what we're trying to communicate here is we should have some kind of factorization where in one factor, everything involving variable x is to one side, and the opposite factor should only involve variable y. So let's take a look at how to make that happen in this particular problem. Well, it says to just find the general solution. And this problem goes z prime is equal to e to the t plus z. So that's our differential equation to solve. This is kind of an unusual differential equation in the sense that if we want to write it as a separable equation, we really need to force in Leibniz notation first of all. So Newton's prime notation should be ditched as a very first step. So we can convert this to dz. Z is now going to be treated as the dependent variable, and down below we'll have to use dt, which is the second variable in the problem. So that'd be the conversion. Then we can write this as e to the power of t plus z. So the next feature of this problem is that is unusual is we need to force in some kind of factorization. So we have to factor e to the power of t plus z somehow. So variable t, x in the formula over here, and variable z, y in the formula over here, are completely separated in the factors. Anyone see how to factor e to the power of t plus z in that way?
Isn't it just like et plus ez?
Yeah, exactly. We just use law of exponents and the factorization is done. It's one of those things where if you don't look at it just right, I could be staring at it for quite a while. But by laws of exponents, that's our factorization. So we can think of the e to the t as playing the role of g of x, and e to the z as playing the role of f of y. The left-hand side is still dz dt. But something subtle happens when we write these out. Here we're talking about the ordinary derivative, which is a limit of the difference quotient. But here and here, we're now thinking of differentials, where dz and dt have independent meanings. So we can rearrange this to write, now we have dz is equal to e to the t times e to the z dt. So we're starting to not only factor in terms of one variable and another, but we're also going to start separating things. We want on just one hand of the equation, everything involving t. The other side of the equation, the left-hand side, should only involve variable z. So we can multiply both sides by e to the power of negative z to get e negative z dz equals, multiplying on this side cancels it, so it's e to the t dt. So the formula so far tells us whether or not the equation is separable, which is really important when we have multiple methods working at the same time on an exam situation. The definition doesn't tell us how to solve it. Once we have this separable equation, we have to first put everything with one variable to one side, everything with the opposite variable to the other, and then what would you say should be the very next immediate step after that?
Get rid of A.
Not quite get rid of A.
Antiderivative, right? Or integrals on both sides?
Yeah, if we take the antiderivative of both sides, then we'll have an equation that does not involve the differentials dz and dt. So let's take antiderivative of e negative z dz set equal to the antiderivative of e to the t dt. So that would be the format. Then sometimes these antiderivatives can be involved. Material from 7.1 through 7.7 could possibly be used. But in the context of, say, exam 2, I wouldn't throw something like a trigonometric substitution in the middle of this. That'd just be nasty. Can happen in the homework because homework is for the sake of practice. So on the homework, some of them are a little bit nasty, but this would be a decent exam type problem. So next we get the antiderivative of e negative z. It would be itself, and because of the chain rule, we have to multiply by -1. So that would be the full antiderivative of the left-hand side. Right-hand side is even nicer. It would be e to the t, and right at this step, we must add the constant c. We would say at this stage, the differential equation is essentially solved, but the tragic part about it is it's now in implicit form. So the ones that we can solve for, we must solve. And the variable we would solve for is the dependent variable z itself. Yeah, question?
So why do you not add a constant to both sides? Because you're taking antiderivative of both sides, so why not add a constant to both sides?
You absolutely could, yeah. So what you could do as an alternate approach, let's do that on this one. You could go e negative z, or negative of e to the negative z, plus, I'll call it a c1, is equal to e to the t plus a c2. Then what you could do as an immediate next step is write negative e to the negative z is equal to e to the t plus c2 minus c1. Then the issue with c2 and c1 is they're completely arbitrary constants. They can both be any real number. So what we could say is an immediate follow-up step to this line, negative e to the negative z is now equal to e to the t plus just a general constant c, where this constant c is equal to c2 minus c1. So if c2 and c1 are allowed to be any real number, we can substitute it with some other constant c itself, which is any real number. And typically that's what people end up doing. They're just going to, after they take the antiderivative to both sides, only write that constant c and imagine they absorbed both constants into one. Does that make sense so far about the single constant? Okay, so in that case, once we get to here, we can solve for the variable z as soon as we take the natural log, but this negative will cause some issues. So I'd probably say multiply both sides by -1 to get e to the power of negative z is equal to negative e to the power of t plus, or rather minus, c1. or c itself, this one right here. Now we can take the natural log of both sides. To write natural log of this side is now just negative z is equal to the natural log of negative e to the power of negative t, or that was positive t, minus that constant c. So we're on our way, and you might see in the back of the book solutions to some problems that they could have written plus c, which seems like a completely algebraic mistake, but once again it's valid as long as they add a little extra detail. They could say C3 is negative C1. So essentially the same trick. If C, or that was C itself, if C is any arbitrary constant, then negative C is an arbitrary constant as well. So you might see random results like this in the back of the book solutions. But finally, as soon as we multiply both sides by negative 1, z would be negative of the natural log of negative e to the t plus the arbitrary constant c sub 3. And that would be the general solution to that problem. Any questions with that method so far? Yeah?
Inside the natural log, wouldn't it be absolute values instead of parentheses?
I think what you're thinking of is the situation where if you were to take the antiderivative of something along these lines, a 1 over x dx, in this case we're looking for the most general antiderivative possible, so we would have a natural log of absolute value of x plus a constant. But this time what we did with the natural log was a little bit different. We just applied the natural log to both sides of the equation. In that situation, we wouldn't have to use absolute values, only in the context of taking an antiderivative type step. Does that make sense with the absolute values? Cool. Other questions so far with that problem?
Well, it's more of a
Yeah.
college algebra question, but why was it preferable to multiply the bottom step of that middle row
Oh, yeah.
to take the natural log of a positive e to the negative z, and then
I got what you're saying. Yeah, we tried to dodge the negative here. I said that it would cause problems if we left it in, and maybe that's not completely right. What you could do is say, well, it might cause problems actually. The natural log of negative e to the power of negative z, if we tried to work this out, one issue we're going to have is that this constant right here, e to the power of negative z, would have a graph that looks about like this. It's going to be decreasing exponentially. That means if we throw a negative in front of it, it's always going to be a negative value, and so it'd be undefined in the natural log function itself.
okay, so whereas e to the positive t is fine.
E to the, this one right here?
Yes.
That's a good question. It would depend on that constant of integration there. So whatever c is, it's going to shrink the domain of the solution curve for z. So if C3 is, say, 100, the domain of the variable t is only going to be so large so that this whole thing is still positive for a solution curve.
Gotcha.
But yeah, that causes all sorts of little domain range type issues when we play around with these kind of things. Other questions about that so far? Okay, so let's maybe try a different kind of problem. In this problem, we're finding the general solution. And by general solution, we mean we really have a whole family of different curves with different domains due to the issue with the natural logarithm requiring positive results. But sometimes we seek a particular solution. So let's take a look at what initial value problems would look like in this context. But other questions or comments first about this version of the problem? Okay. So if you see something along the lines of solve the initial value problem, sounds like a totally different sort of problem, but it's really the same sort of steps with an extra type of move we have to make at the very end to solve for the general constant of integration. So the problems look about like this. They say, solve the initial value problem. And let's pick a good one. How about, I mean, they're all good. Let's start with dy dx minus the natural log of x divided by xy is equal to 0. So that would be our differential equation. What makes it now an initial value problem is the further condition that we want the particular solution to pass through y of 0 is equal to 1. In other words, we want to pass through the point 1, 0. So we're going to do essentially the same thing and then solve for the constant. First things first, though, is we want to get it into a format where we are about here. This is essentially the goal of every single separable equation. Separate everything involving one variable to the left and everything involving the opposite variable to the right. What would you say the first step ought to be then to get to that point of here?
You add x divided by ln x to the other side, or I guess.
I think that would, yeah, we could just move it to the opposite side, and then we would have something that looks about like this right here. So let's say, add this, natural log x divided by xy, to both sides, and this would be our new equation. We didn't have to worry about converting something along the lines of y prime to Leibniz notation. So immediately we can say multiply both sides by dx. We'll have dy is the natural log of x divided by xy is equal to dx. Then it's almost settled. We just have to kick out the variable y on the right-hand side by multiplying y to both sides of the equation. But any questions to that? Any questions about that step so far? Okay, let's multiply both sides by y. Now the equation is y dy equals natural log of x divided by x dx. Then the immediate next step, once we have everything separated, is find the antiderivative of both sides. So now we're integrating. So let me copy that up to here, because we're definitely going to run out of space. So we have that y dy is now equal to the natural log of x divided by x dx. So we'll take the antiderivative of both sides at the same time. Then we just have to make a judgment call. It's completely fine to add both constants here, but typically you'll see a lot of people, well, they just get lazy, if we're being honest, and they just keep one general constant, imagining all constants were absorbed into one, into the right-hand side. So if I was going to solve this, I would just write y squared divided by 2, the antiderivative of the left-hand side. Antiderivative of the right-hand side would involve a u substitution, so let's do that next. So for a natural log x divided by x, a good choice would be just natural log x itself, since now the differential of this would be du is 1 over x dx. And 1 over x dx is precisely what we have on the integral on the right-hand side. So we take this differential equation, leverage it to solve this differential equation to obtain the antiderivative. 1 over x dx is now du, and natural log x will be u itself. So that's an antiderivative we've essentially done before, just a different variable. We have y squared divided by 2 is equal to u squared divided by 2. Then this is the critical step. Once all antiderivatives are solved, add the arbitrary constant. So we're about there. Any questions to that step so far? Okay, just like in a problem in chapter 7 in finding antiderivatives, our solution must involve just the variable y and the independent variable x. So we must undo any substitution that we've made. So now this becomes y squared divided by 2 is equal to the natural log x. And we have to be really careful writing this, because writing natural log x squared in that form has a completely different meaning. So if you want to square the natural log of x, maybe the safest way to write it is in this format, so that we don't confuse the variable being squared as opposed to the entire function of that variable being squared. This is all then divided by 2, and we add a constant. What we can then do is, let's just start solving for y. Then at the very end, we'll find this, use this information to solve for the constant. But if we want to solve for y, maybe let's just double both sides of the equation. This would become y squared is equal to the natural log of x squared plus, I would write just a c1. There's no harm in writing 2 times c, but the algebra is going to start getting messy once we bring in the initial condition. It's much nicer to say that we have a new constant of integration C1, where C1 is twice C. If C is any real number, then C1 itself is also any real number. So we're just essentially doing a substitution to simplify the algebra. Then the very next step is take the square root of both sides. I'm probably going to need a new column. Don't worry, I'm not dying. I sound worse than I feel. But now let's take square roots of both sides. So this would become y equals, because we're taking a square root, we have two possibilities. It's either the positive or the negative version of the square root of the natural log of x squared plus c1. So we've solved for y, but the trouble is, in this implicit form, there's really two potential functions, y, that we could have. And we have to decide which one it ought to be, either the positive result or the negative result. Anyone see which one it must be? The trick to that is the initial condition that we've been sort of ignoring the whole time. We insisted whatever our solution curve y comes out as, we must have that y at 0 is equal to 1, which is a shorthand of saying in the function notation, when x equals 0, y must come out to a positive 1. So if I were to input, oh, y of 0 is equal to 1, I might have got that backwards. That doesn't look too good, does it? So I have natural log x divided by xy. It should have been y of 1 is equal to 2. Sorry about that. Let's throw in a new initial condition because you can't let x be 0 there. The natural log of 0 itself is completely undefined. So let's try this out again. So we want y of 1 to be equal to 2. So y would be equal to 2 when x is equal to 1. That looks a little bit better. We can't throw a 1 inside the natural log problem. If we threw 1 inside here, this would all be 0. And we're told that y has to come out to a positive 2. That means the possibility is just the positive root because of the positive here. Does that make sense so far? Okay, if we said that y at 1 had to have been negative 2, we must take the solution curve that involves the negative square root. So now we know that y itself is now positive natural log of x squared plus the constant c1. Using that, we can now input when x is 1 and y is 2 into this entire equation and solve for that constant c1. Now we'll get precisely one single answer to this process. So now when y is 2, inputting 2 there, we're going to input 1 in for x to get the root of natural log of 1 squared plus c1. But natural log of 1, again, comes up quite a lot because problems tend to be rigged to come out nice. What would natural log of 1 come out as?
0.
Yeah, so this whole entire quantity is just 0 itself. So now the problem is reduced to 2 is equal to the square root of c1, and if we square both sides, we have 4 is equal to c1. So now at this stage, we can say the particular solution to the initial value problem is y equals square root of the natural log of x squared plus c1, which we found to be 4. So that's the only curve that satisfies the original differential equation, way over there, and also satisfies the revised initial condition, y at 1 is equal to 2. Any questions about that so far then?
In what conditions do you have to substitute back the C1 to the C, the regular constant, or do you not have to?
In this context, you would not have had to.
So when would you have to?
In the context of differential equations, you would essentially never have to.
Oh, okay.
Yeah, if we have an arbitrary constant, any kind of multiplication like this would get absorbed into it. And so you're completely fine to always just leave it as a C1 in the context of differential equations. If you did undo the substitution, what would happen over here is you could call this a 2C. So this would become a 2C right here, we square both sides and get that 2c is equal to 4, so that 2 would be equal to c itself. But then over here, we'd have a 2c at the same time. So if c is 2, this would still convert to a 4. So if this c1 was left as a 2c, in either case, we're just forced into getting a 4 itself.
Okay.
So it's really just by the nature of c being an arbitrary constant. We will only really do the substitution of c1 just to simplify the algebra a little bit. Other questions about that so far? Okay, so these are two versions of the separable equations. They're both versions where things just work out really, really nice. But the field of differential equations does get kind of terrible, so it would be disingenuous to not do a terrible one. So let's do one that's really horrible next. Any questions first before we try it out? Okay, what makes this one interesting is we're just forced to use the fundamental theorem of calculus, part 1, which is not something we use very, very often, but in differential equations, it gets used pretty routinely for a lot of problems. And this problem says to find or solve the initial value problem, which reads y prime equals e to the x squared divided by y, and carefully either write initial condition y at pi is equal to the square root of 7. So that's what we'd like to solve. And things like this do come up pretty routinely in actual bona fide real-world physical situations, so they're valuable things to see how to deal with. First, let's take a look at the statement of the fundamental theorem of calculus part 1, which says if you have a continuous function and you're off to integrate it, say if f is continuous, then what we could do if we want to antiderivative of f itself is write a function called g of x. G of x will be a definite integral from a. A just has to be in the domain of the function. It doesn't necessarily have to be that left boundary point. And the independent variable x would be the upper limit of integration. What's nice about this function is, after doing a lot of work, we'll find that the derivative is, in fact, f of x. So if we take this as our function g, then g prime of x is f of x. It tells us that this is an antiderivative of a continuous function. In other words, every continuous function, no matter what, no matter how terrible it looks like, it will have an antiderivative in this format. So that's what we're going to do to get through this problem. Any questions before we give it a try? Okay, so let's first separate the equation as before into two parts. So we have, instead of y prime, we'll do dy dx, or yes, x, is equal to e to the x squared divided by y. So let's take two steps at once, multiply both sides by y, so that we'll have a y dy, multiply both sides by dx, so that we'll have a e to the x squared dx. So that's the setup so far, and we know that at this stage, the time is right to find the antiderivative of both sides immediately. So we can say antiderivative of y dy is antiderivative of e to the x squared dx. Left-hand side we've done something like 3 times already today. Antiderivative of a variable is that variable squared cut in half. This is the problem. The antiderivative of e to the x squared, what would you know about, anyone know any interesting facts about that particular antiderivative? One terrible fact that our author talks about in this book is if you seek to find a closed form solution to the antiderivative of e to the x squared, something like this would be a closed form solution, you'll find it's actually impossible. And there's loads and loads of problems where that's the case. For example, we can do x sine x by parts. It's completely fine. It's a nice, good warm-up problem. However, sine x divided by x is impossible. Any tiny little change in all of these problems can really wreak havoc. So we need something other than a closed form solution of the antiderivative. And that's where the fundamental theorem of calculus comes into play. So from here down to here, by the fundamental theorem of calculus, part 1, we can say the antiderivative of e to the x squared, feels like a cop-out, but it's really necessary, is the function g of x. So we're going to build a function that has an upper limit of integration x itself. The lower limit of integration doesn't necessarily have to be a. That's just how we chose to write it in the formulation of that theorem. It can be anything in the domain of e to the x squared. But the domain of e to the x squared is all real numbers. But there is then still one further important trick. If we want to solve the initial value problem, we should pick this right here for our lower limit of integration. If we pick anything else, we're going to have to work really, really hard with some Simpson rules. So let's throw pi down there, coming from the initial condition. Inside, we're going to write an f of t in that g function. So that'll be e to the t squared dt. If we wrote this, it means we found an antiderivative. It just is kind of an ugly one. It's the best we can do. But because we found an antiderivative, we'll add the constant of integration immediately at that step. So that's a kind of a strange step to take, but we know by the fundamental theorem of calculus, part 1, if g of x is the definite integral from pi to x of e to the x squared, well, that would be a variable t, dt, then the fundamental theorem tells us that g prime at x is all of this with the variable x itself. So we have, in fact, found the antiderivative of e to the x squared, just in not the most savory way. It is what it is, though. And in the course of differential equations, that's just something we have to settle for sometimes. But any questions to that step so far? Okay, so we have two things to do still. We need to solve for y, and we also need to solve the initial value problem. So let's now multiply both sides by 2. Y squared then becomes twice the definite integral from pi to x, e to the t squared dt, plus, I'll call this a c1. This would be multiplied by 2, and we can say that c1 is twice c. You don't necessarily have to write this out all the time, but I think this is a really good practice, because if you take differential equations, depending on who you take it from, some people will call that a required step to track what is happening with the constants. Next, we'll take the square root of both sides. When we take the square root of both sides, we once again have to resolve will we use a positive or negative root. But really the punchline to that is the output here. If this output is positive, we'll take a positive root. If that output is negative, we would have taken a negative root. So simply due to the positive here, we can say that y itself, well, we need to clear out more space first. Needs to take a lot of space. Y itself would be the positive root. I'll just put a plus here only for emphasis to say where the sign came from, of the twice the definite integral from pi to x of e to the t squared dt plus c1. So we've done it. We've found the general solution to that differential equation. Every solution would have this form. Well, really plus or minus. When we picked plus, it's because we're now going for the particular solution that satisfies y at pi is equal to the root of 7. Which implies that when x is pi, we have the output y equals to the root of 7 itself. So we're going to take the same step as before. It looks awful, but we'll put root 7 in place of y, set it equal to the root of. Everywhere an x occurs, we'll throw in a pi itself. So we'll take twice the definite integral from pi to pi of e to the t squared dt plus c1. So now this lower limit of integration, we could have been very flexible with. You could have, in fact, picked any real number, and it would have been a bona fide antiderivative. But pi was required because when we threw in pi, coming from the initial condition in the initial value problem, we now have a very nice integral. What would you say the definite integral from pi to pi is of any function? It looks kind of weird, right? Well, let's suppose you had something that looked like this instead. From pi to pi of, let's just do something nice. Let's say it was just an e to the x dx, something we can definitely integrate. Antiderivative of e to the x would be e to the x, but now we evaluate it from pi to pi. So having the lower limit and the upper limit identical means it would be e to the pi minus e to the pi. It would automatically be 0 itself. But this would just be an example to illustrate what happens in general. A definite integral where the lower and upper limits of integration are identical always evaluates to 0. So that means we get a really, really fast integration if we pick the lower limit of integration just right from the initial condition. So this becomes 0 itself. We can say that the root of 7 is now simply the root of c1. Squaring both sides tells us 7 is c1. So finally, we can state the solution in one go. The solution to the initial value problem is y equals the square root of twice integrate from pi to x of e to the t squared dt plus 7. I'll circle that just to emphasize that would be the answer to that problem. Any questions about that kind of problem so far? Definitely is a little bit weird. And if this was, say, an exam problem, what I would include in the instructions on the exam, just to keep all sane, is I would tell you immediately you must use the fundamental theorem of calculus part 1. That way you're not spending too much time trying to integrate something that's going to be impossible. I'll let you know that this is the necessary approach on that particular problem. But other things you might say is, if you look at that curve that's circled there, suppose you wanted to graph that curve. Anyone see what the challenges could possibly be to that? I mean, a calculator will do that. If you load up something like MATLAB, Mathematica, they'll plot the solution curves, no troubles. But what is the practical problem of trying to plot that thing by hand? There's an integral, right? So if I were to try to plot this curve, I mean, I would probably say start with a table of x and y, pick x as something like, I want to pick pi, but maybe 2 pi. Then I would have to put 2 pi here, and I would have to do that integral, which means I would try to use the fundamental theorem of calculus part 2 that requires an antiderivative in a closed form solution. This would be no good to us. So we would have to take this and hit it with, say, the trapezoid rule or Simpson's rule or something along those lines. So if we have to evaluate the function, then we would have to do this integration numerically because there is no closed form answer to this as an antiderivative. So we still need a better way to get through this because this as an antiderivative is just kind of nasty. And this is the whole purpose of chapter 11. Chapter 11 is going to give us antiderivatives that are a smidge better. They're still kind of nasty if we're being fully honest, but they're a little bit more useful. And in fact, in the course of differential equations, the material in chapter 11 does become necessary for many, many equations. But any questions then so far with that terrible one? Yeah.
Is it possible just to plug in your x and y where instead of taking the square root, just where it says y squared?
Oh, yeah. You could have done it right here as well. Absolutely. And sometimes that's a better approach because if I do it at the very end step on every single problem, it becomes a good amount of algebra that's going on inside here. So sometimes this is the simpler version, and you could have said that when y is root 7, go root 7 squared, you would get 2. We're throwing in pi for x, so that whole thing goes to 0. So we would have 2 times 0 plus c1, and we get the same result. And I think that does look a lot cleaner doing it right immediately at that stage as well. So you do have options of when you decide to solve for that constant. Other questions about that so far? Okay, so that's kind of the worst case of these types of problems. Let's go off then to maybe one more kind of a routine problem. Then we can start the next section if people feel up to it. Or if people would rather, we could look at a couple versions of applications. One of them is a half-life problem, essentially the opposite of the population growth model we looked at last time. Another one is some interesting stuff from physics, which is actually quite interesting. For example, think of a boat moving through water. That sounds exciting. So we can maybe do one more like this and an application. Does that sound all right to folks? Okay, so let's decide on one more. I want to do one that must be left in implicit form so that when you're doing the homework problems and it says leave problems 5 and 7 in implicit form, you know what to look for. So this next one is going to be dy d theta equals e to the y sine squared theta divided by y secant theta. It looks kind of nasty because there's lots of parts going on, but keep in mind this one, which didn't have too much happening, was really the nasty one. A lot of these problems are rigged to work out a little bit more cleanly. So first step we are going to take is keep variable y on the left-hand side. So we'll have dy kept to the left. This y has to be multiplied to both sides of the equation. So we'll have a y in the numerator. Similarly, I'll multiply both sides of the equation by e to the negative y. So I'll have y e to the negative y to the left. So that takes care of these two portions. Then we multiply d theta to the right-hand side. And sine squared theta, secant theta, can stay just the way it is. So we'll have sine squared theta divided by secant theta. So that's our setup so far. Once we have everything separated, we can immediately take the antiderivative of both sides. Any questions to that step first? Okay, so if you want, you could just hit it with the integral immediately. Then that's the right format for the definite integrals. Sometimes these can be a bit challenging, but we're not going to get too out of hand. This one can be solved. What would you say the method should be?
Parts.
Yeah, what's interesting is if this was negative e to the y squared, we could have done it by substitution. If it's this, now it's impossible and we have to go with that route. But if it's this, integration by parts would do the job. So let's do this left-hand side by saying u is going to be equal to y. dv can be e to the negative y dy. And I picked it in this way because the u variable you choose ought to simplify when you take its differential. And the differential of e to the negative y, in fact, gets a little bit worse. You get an extra negative sign. So we can write next du is dy, and v would be equal to, it's the antiderivative of this, so we go e to the negative y, and counteract with a constant negative 1 to account for the chain rule in our check. So that's going to resolve the left-hand side. The right-hand side looks a little bit messed up, but remember secant is really just 1 over cosine, so you can say that sine squared theta divided by secant theta is really sine squared theta times cosine theta. If you move the reciprocal function to the numerator, in other words, you get the ordinary cosine function. So that'll be helpful for us to solve the right-hand side. So let's go off to a new column and solve both of those at once. First, we're focusing on the left-hand side where the method is by parts. So we'll take y times e to the negative y. So negative y e to the negative y. Then we'll multiply this way by taking negative the integral of those two quantities. So it'll be minus a new integral of negative e to the negative y times dy. So that's our entire left-hand side, nearly resolved. The right-hand side, we're using this trigonometric identity to get through it. So let's just copy sine squared theta, cosine theta, d theta. And that's where we're at so far. Any questions to that step? Okay, so the next thing we're going to want to do is, here we can factor out the -1 and call this all a positive constant. Then take the antiderivative of e to the negative y, but we've in fact done that once already. So this converts to negative y e to the negative y minus e to the negative y equals, then we need to handle this right here, but this takes us all the way back to section 7.2 in January. That feels like a really long time ago already, but these were all solved by a particular u substitution. There were tricks to this though, to pick the right one immediately each and every time. The trick was, look for an odd power. If you don't find an odd power, you need half-angle identities, but that's our odd power right there. Then the u substitution involves the opposite function sign. So I'll let u equal sine theta, then we'll see if it works. Du would be cosine theta, d theta, which means this entire quantity is now a du. So that looks like that's going to do the job. And if you don't care for tricks like that, it's really no harm to just try something and see whichever one works. It's usually pretty fast. So we can come back over here and say that this is now the antiderivative of sine squared. Well, u is sine theta, so that's a u squared. Cosine theta d theta is du. And we're just about solving all of those antiderivatives. There have been a lot of them. So next, antiderivative of u squared, first let me copy negative y e to the negative y minus e to the negative y equals, power goes up to u cubed divided by 3, and I would add the arbitrary constant at that step. So we're just about there. Last thing we need to do is, we must say what the variable u is. So undo the substitution gives us negative y e to the negative y minus e to the negative y equals sine cubed theta divided by 3 plus a constant. Okay, so that's our equation. It's nice that this equation is not an initial value problem, so we don't have to worry about solving for the constant c. But the next thing that we would like to do normally is we would solve for the variable y, if it's a tractable problem. However, a lot of these problems, well, not a lot of them, 2 of them in particular in section 9.3, is going to look about like this. If we try to solve for y, it might be doable if it looked like this, but throwing a variable y next to e negative y massively complicates things. So it might be solvable for y, but I don't have the particular repertoire to come up with a method immediately. You might have to use crazy methods like, say, Newton's methods and so on. But in this situation, we would call this the general solution in implicit form. And sometimes we just have to settle for that. Sometimes solving these things really is a very, very nasty problem. There may not be a single solution for the variable y. There could be infinitely many different solutions, for example. So we're just sometimes settling for the implicit solution. So if you're doing problem 7, 5, or 7, that would be the stopping point. Any questions about that so far? So these last 2 problems have been kind of the worst cases, where occasionally you have to invoke the fundamental theorem of calculus. I don't think I assigned any of those in this homework set, but in 9.5 we'll have probably 1, possibly 2. The other situation that it comes up is sometimes the implicit form is the place we have to settle for on an answer, but most of these problems are pretty quick and follow this really same approach, where different styles of antiderivatives, different methods could come into play. Any questions so far then about these kinds of problems? Okay, maybe we can end with an application then, if folks would like. We have 2 versions that we could look at for an application. Either looking at something from physics, or something from, I guess you could say, nuclear engineering, half-life. Which problem would you folks like to look at for a final problem of this section? Or we could say do 1 problem for the next section to work ahead. I'll let it be student's choice. So should we work ahead a little bit or look at an application? Application? Sound fun? Okay, then I'll leave it up to you folks. Should we do the strontium-90? I'm not sure if that's the naughty stuff or medical stuff, or we could do something from physics. Anyone for the physics one? Okay, let's give this one a try. So this one is quite a bit different from what we've seen so far. It tells us in this problem, let me zoom in just a bit, we have an object of mass m moving horizontally through a medium which resists the motion with a force that's a function of the velocity. So they say the force, capital F, is a function of velocity. Velocity is mass times, well, force is mass times acceleration. Acceleration is d2s dt2. S is the position of that object, and we're taking its second derivative. The first derivative would have been the velocity. Second derivative is the acceleration a. So we can say mass times dv dt is equal to F times v, or F of v. So the force as a function of the velocity is now taking all of this and forcing us to focus on this quantity right here. Then there's a lot of information in this problem. They say v is a function of time. S, that's just the position of the object at time t, also a function of time, represent velocity and position of the object. For example, think of a boat moving through water. So maybe it's fighting a current or something along those lines. Now we're told, suppose the resting force is proportional to the velocity. That is, F of v, this quantity here, is negative kv. That's similar to how we set up our population growth setup. Something being proportional to the velocity gives us a proportionality constant k times velocity itself. So they tell us this model is appropriate for small values of v. This comes right out of our textbook, so you can write a letter or email Mr. Stewart to see what small counts for in this particular setting because he doesn't provide those details. We're going to say that v of 0 is v naught, the initial velocity. S of 0 is the initial position. We want to determine v and s at any time t. Essentially, they're telling us, find the velocity function v at t, find the position function s at t. Then, if we have time, what is the total distance the object travels after time 0 in this model? So, sounds like an exciting problem. Where it starts is right here. So this is the good stuff. Let's put that on the chalkboard. So we have that mass times dv dt. This is really just mass times acceleration, since the derivative of velocity is acceleration. So the left-hand side is force, is equal to F at v. But we imposed a new situation in the problem. Suppose the resting force is proportional to velocity. So now F at v is equal to negative kv. So mass is equal to dv dt is equal to negative k times v. So that's our setup so far. Kind of an interesting problem, but any questions to that step at the moment? Once we get to this stage, however, keep in mind that we're just leaving this as a v, but v is really a function at time t. So we need to bring this, we need to leave it precisely where it is, because as we separate, dt is going to go to the right-hand side. K is just a constant, so we could leave it alone, or if it annoys us, we could just move it over to the opposite side. It's really up to us. Mass itself is also constant in this problem, so there's no crazy relativistic effects going on. So let's divide by negative k, just for convenience, to get negative m divided by k is equal to, we're also multiplying by dt, so v dt, oh, and I miscopied. dv is still alive over here, then it's equal to v dt. Any questions with that so far? Okay, then we need to take the antiderivative of both sides at the same time. So this is what we would be looking at. So the antiderivative of the left-hand side, well, all this is really just a constant altogether. So we would have over here negative m over k, and this should just be a dv. Does that look all right to that step? Or hang on, that should have been a t, rather. How about that? Does that look a little bit better? So we have negative mk, m divided by k times t on the left-hand side. On the right-hand side, we need the antiderivative of velocity with respect to time. That's concerning because when we separate things, keep in mind, this is no longer a variable v. If it looked like this, antiderivative of v dv, and we thought of this as simply a variable, we could write v squared over 2, and everything's fine. But v is a function of time, and we're integrating with respect to time, so we need to be a little bit more careful. So let's take a look at that integral over here. So we want the antiderivative of v dt. We just have to remind ourselves, what is v really? It's the velocity which depends on time t. But velocity is also the derivative of the position function s with respect to t. So if I take the rate of change of the position, ds dt, that would give us velocity. Then we throw in a dt here. And that's the antiderivative that we must take. So antiderivative of ds dt. It's saying, I want the antiderivative of the derivative of the position function. What would you say that should be? Yeah, exactly. So we have essentially a cancellation. That's not a bad way to visualize it. That essentially, this just becomes s of t plus some constant. So we have the position function s of t popping out on the right-hand side. So it is a s of t plus some constant of integration. Does that look all right to folks so far? So let's look at how we started this. We looked at this as a differential equation, mass times acceleration, dv dt. Then we said f is equal to negative kv, f at v, and we had to separate things involving variable t. Keeping in mind this v of t really involves variable t itself, and this is where we're at, s of t plus c. We also had the initial conditions that v at 0 is v naught, and that s at 0 is s naught. We were never told the values of v naught or s naught, but now we can use these values to start to solve for this constant here. So let's do that very next. So if we input, say, on this initial condition, this is saying at time 0, the position s would be equal to s naught. So we can throw in here, at time 0, we have wiped out this left-hand side, would be equal to s of t would be s of 0, or s naught, plus the constant of integration. So now we can solve for the constant by subtracting s naught from both sides. Does that make sense to that step? Okay, so let's subtract our s naught, and we can say the constant of integration c is equal to negative s naught. So we can now take this entire equation here and convert it to negative m divided by k t is equal to s of t plus the constant of integration c, which is equal to a negative s naught. So finally, the instruction said to, where is that? Determine v and s at any time t, and this is our function s at t. So we can take and write s of t is going to be equal to, add s naught to both sides, then it'll be plus m divided by k times t. So that would be the s of t function so far. Provided we've done everything right, that seems kind of fishy to me somehow. I'm not completely happy with that. How do you folks feel about these steps to this stage so far? Yeah?
Wouldn't it be minus m over k?
Oh, yeah, that's right. So this should have, I added s naught to this side, and this is still a minus. Yeah, thanks for spotting that. Still, that feels a little fishy to me. But questions so far to that step? I feel like something is missing here. I was not expecting to get s of t at this step. I was expecting to get velocity and integrated. I feel like there is a mistake somewhere inside this. Probably a cold medicine inspired type mistake where I'm not going to see it right away. Anyone see what it could possibly be? We might have to come back to this one, because we feel like this might not be the correct result. It may not be a lot of benefit to go too much further, but I feel like something was missed inside here. K was the proportionality constant. We had mass. We separated by moving K over, leaving negative KV. I might have to think about this one, but there's something fishy going on with this problem. I feel like it should have came out a little bit different. But if we feel okay about this, we could have gotten the velocity function, v, by taking the derivative of the position function s. But notice then velocity is constant, and that also sounds concerning. That would give an acceleration of exactly 0. So something has gone a little bit awry somewhere along those lines. Might have to do some homework on this one. I'll let you folks know what the issue might have been. Highlight in red or something like that. But I think this might be a good stopping point, since my voice is starting to crack and this does not look quite right. We'll definitely come back to it. I might be just post something as a PDF on the Moodle site to say where this has gone awry. I feel like it's gone awry somewhere. But any questions so far, folks, before we call it a day? Okay, well, I hope you folks have a good weekend. Next week will be midterms week, but we do not have an official midterm in this course. We have, say, third terms with 3 exams. But I will nonetheless still upload a midterm grade to the Bengal web, which will be close to what you've seen on your course score on the first exam.